Hello, welcome to the today class. Today we'll talk about some of the recent image search technique that works with the deep learning. So these are the today class materials. We'll talk about recent CNN-based approaches that consider different regions, also the attention. Also, we'll see how we can compute the local descriptors. And we'll talk about some other, we'll briefly touch on some other applications based on the image search. And before we move on to the today topic, the last time we talked about the unsupervised hashing techniques that are based on the hyperplanes, also the hypersphere. And we talked about the supervised techniques using the deep learning techniques. Also, I think the TA upload the specs of the PA2 at the home page. So the main idea of the PA2 is that you need to apply this binary coding embedding, also inverse index, to this implementation that you did for the PA1. So you can use simple k-means or the product quantization for the inverted index, and also you can just using this spherical hashing or the product quantization for the binary code embedding hashing technique. So there are a lot of available resources. So actually, I recommend you to apply those source codes so that you can very easily actually implement some of the components of the PA2 instead of instead of implementing everything from scratch. Okay, so I'd like to talk about today's material. Actually, I talked about before that this AlexNet, actually the CNN-based CNN-based technique actually there showed this dramatic improvement on many of these computer vision techniques. So basically, the main reason why they achieved a very good result is that they were able to utilize a lot of this training data set. Especially, they got this about 1.2 million the labeled image for the ImageNet, and then they were able to use the GPU with some of the improvement in terms of the deep learning. They can use rectified ReLU unit, also some other these techniques. And actually, these are they applied their deep learning technique and showed a very good result on some of the classification techniques. After that, since then, actually, there are a lot of the researchers and try to apply the CNN technique to the various computer vision and many other related problems. And these are actually one of the early work on utilizing this deep learning CNN-based technique for the image search. Basically, this is actually very similar this network architecture to this AlexNet. They used a lot of the convolutional neural net layers, the CNN layers, and then what they observed is that some of the layer under the low level layers actually those layers are kind of corresponding to this low level features like the extracting the edges, something like the edges corner. And then they also identified that some of the layers in the upper ones actually they are more or less related to the semantic features. So they say that they tried out different layers, and then for the case of the image search, they say that some of the upper layer, like layer 5 and layer 6, in this architecture, they used those features from the layer 5 and layer 6, and they mentioned that they got a reasonably good image search accuracy. So actually, they say that those features, they used those features as a neural code for their image search. And then basically they used in that paper they talked about some of the sampling, also the centering priors. So they say that they just use the convolution layer, the features as a kind of local feature, and then they sum all those weight of the convolution layer as a feature. Here actually I got the sum of the equation. Basically it's nothing but they just aggregating some of the older features across all the images to compute their neural code, which is actually kind of their image descriptors based on CNN. And actually here I got I I got the table from that paper. You can see that actually here actually they tried out their approach across different data set, and they got this actually sampling without centering prior. I will talk about centering prior here. So actually they do the actually sampling. They achieve the very good accuracy here. You can see that as we get the higher the value, you can treat the actually the result from the image search technique actually accurate compared to the actually this ground truth of that query image. And also they consider some sort of heuristic approach. They consider also the centering prior. It means that if you look at the image, obviously there a lot of in most of case, most important objects may be located at the center of the image, right? So they consider some sort of the higher weight under the feature that expect from the decentering region of the image. So basically, instead of just equally summing up all the feature, if the feature coming from the center, they use the more higher weight. So actually, basically they consider some sort of the weight sum with the higher weight on the center in the around center region of the image. So that's actually the sampling technique with the decentering prior. So depending on the data set, in some of data set, the technique without this centering prior, that's a heuristic, right? They got the better accuracy. But in other data set with the decentering prior, they achieved higher accuracy. So actually, they suggest that basically aggregating the aggregating weight of convolution layer useful for the image search, and then they also suggested some of the heuristic. Obviously, you can see that they computed in a way they just utilizing this feature that are computed from kind of AlexNet that are computed from the ImageNet, right? And then for that case, actually their main task for their training was actually the classification. So it wasn't really those features were not really dedicated for the image search technique, but they just adopted those features, and then they showed some of the good results, and then they also talked about some heuristic approach. And also these are a little different techniques. So some of the researchers actually thought, we can actually very easily see that if we look at some of the image, right, and then there are some useful information in the image, right, but there will be some sort of the background image, also there is cluttering the background object, right. If we can cut out those region and then consider feature only from the main object, then we can also achieve the better high accuracy, right? Along that line, one can actually think about utilizing this localization technique. Localization actually one of the main components of computer vision. There has been a lot of techniques, but actually there one of techniques. Here I will talk about the faster RCNN. This actually proposed about 5 years ago. Its main idea is that they proposed the region proposal network (RPN) after the last convolution layer. Here, basically, you can treat that there are some sort of CNN architecture. You can see that this may be some of the network architecture close to AlexNet. Also, there are many advanced techniques over this AlexNet. But actually, you can use any kind of CNN model here, and then you actually use the region proposal network, and then which is actually propose a certain region in a way that they wanted to propose a kind of box region in the region where we have higher probability to have object, and then this RPN. The region proposal network is trained to produce the region proposal directly. Basically, we are not going to talk about many other localization paper, but before we have this paper, there are a lot of techniques used kind of the manually designed these region proposal techniques. So there are certain algorithms that consider that actually process image and then propose some sort of the region. But actually, those prior technique were not this deep learning based approach. So actually, a lot of cases to use this region proposal idea, they need to use some sort of external external region proposal idea, which was not this deep learning based approach. But actually, this is actually one of the early papers that proposed the actual region proposal network that can be trained. And then once we got this proposal, then we consider we wanted to extract the feature only those regions, right? And here this ROI pooling, the region of interest pooling is nothing but we extract the feature only on this region from the CNZ feature map, and then based on that we do actually some other classifications, saying that whether we have the object or not for each object. Also, we have some sort of this bounding box. The bounding box, some sort of this regressor. So here actually they also this idea actually comes from some other prior work, but they wanted to adjust this region proposal by proposing some of the more correct is actually the parameter of the box. If you are actually interested, you can also look at this paper. There are many other advanced ones on top of this paper. So here actually the main reason why I like to talk about this fast RCNN is that this is one of the early work that actually proposed this region within the deep learning approach, and then this technique actually also showed the very good accuracy over the prior technique that also used some sort of the external region proposal which one are based on deep learning. And then this technique, this actually the network, right? So it can be run quite fast. So one can actually think about it, adopting this kind of faster RCNN within this image search, right, for achieving the high accuracy. Actually, there has been since actually we have this paper, there are some actually the technique that utilize this kind of concept, this region proposal network. But actually, one of the recent technique that also showing the very good accuracy is that this RMAC technique. This technique is the regional maximum activation of convolution. Its main idea is that basically they consider uniformly general region. So basically, this region proposal idea is that we actually considering kind of the arbitrary region, right? But this paper actually suggests that considering this kind of arbitrary region, it takes a lot of time. Also, it comes with a lot of complications. So instead of that, they wanted to use this uniformly general region. So for example, they used this kind of big box, and then we wanted to extract some of feature and consider those features, right? And then we can also consider this box, and we also do some sort of sliding window the manner, right? And then we can look at this region with the same size of this box and so on, right? Also, we can also think about some other smaller region, right? Basically, as we talked about this merge scale, when you talked about this shift, we can think about it these different levels of boxes with this different size and this different scale, right? And then even at that case, we can also think about a very small box, and then if we consider this kind of small box, there might be the high potential that some of the objects very tightly located within this box, and then if we consider feature along within that box, we might be able to achieve the better accuracy, right? I mean, basically, by looking at the different regions, we can consider feature map that also corresponding better to the certain object located within this box, right? And then each main idea is that they consider this kind of a lot of different boxes, uniformly generated regions with the different scales, and then one can actually as we did for the neural code, we can sum their features, right? But what they propose is that instead of summing up, they say that the maximum activation. So we look at the feature within this box, and then they just use the maximum activation. We just take the maximum value, right? If you look at actually shift that kind of approach, you might remember that we only look at the local maximum, right? So probably this technique, this idea using the maximum activation aligns well with that concept. But actually, I didn't talk about this issue when I talked about this neural code here. This neural code paper. Also, actually, they also tried out. I mainly mentioned that summing up those features as an aggregator, they say that they give the very good result, right? But actually they also try out this max pooling. In other words, within the convolution layer, they look at only this maximum value, right? At the case is actually, if we consider this average pooling or maximum pooling, they mentioned that this average pooling is showing the better results, right? At their cases, they say they found that maximum pooling was not really great. But in this case, so we consider different region and then considering this maximum activation within each region, and then they found that actually this maximum activation gives the better result compared to the other approach. I think that by considering the maximum region, I think that the main difference between this approach and the prior neural code is that we are not looking at this every whole image, right? So since we look at only this region, then there's potential that we actually ignore the background clutter, right? If we just consider maximum activation out of the whole image, right? Maybe in some region from the background, maybe give this maximum activation, right? But within each this localized region, by considering maximum activation, which is actually which has been known for good, which has been known to be good for this translation invariance, right? That's why we also use that concept for designing Swift, right? And then at the case, actually, the maximum activation turns out to be better. Also, there are here actually we need to consider many different uniformly general regions, right? Also, they actually have some sort of acceleration techniques, but I'm not going to talk about here. But if you're interested, you can look at those papers. Also, they mentioned that it will be better if we do some sort of this fine tuning for the image search. So we can use this CNN feature that was trained with the ImageNet for the task of for the task maybe this image this object classification, which is not really related to this image search, right? So in order to achieve the better accuracy for our problem of image search, they say that they retrained actually the network with a task specific data set for achieving the actually high accuracy. So also they identified actually if we do the retraining network with some other irrelevant data set, they also achieve that they can get a low accuracy. So actually it's very important to utilizing the data set that are actually aligned with your well with your target task, also the target data set. So here this is a result different after retraining. In other words, it's the fine tuning. So this actually query, you can see that there are some sort of people within some restaurant, right? Before the retraining, they identify actually this is correct image, but located in the middle in the list, right? But if they do the retraining, actually they can push up their rank to the almost the top. So actually you can see that by do the retraining, the fine tuning with the data set that is actually very similar to the test data set, they can achieve better result. But there's actually initially supported this actually baseline accuracy. If they just using some of their Bayesian actually data set, they achieve this kind of 0.39 accuracy. And then if they are retraining their network with their landmark data set, which is actually very close to actually they tested their accuracy with their Oxford data set, but here actually this landmark data set and this Oxford data set, they're actually very in terms of appearance they look very similar to each other. So they retrained their network with the landmark data set, which is very similar to their test data set Oxford. They achieved their much better accuracy here, 0.5 something like that. But if they do the retraining with some other data set, in this case tunnel view, which is actually not really similar to their test data set Oxford, they got the even lower accuracy. So it's basically main method is very important to you can actually by utilizing additional data set you can improve the accuracy, but it's very important that you use the data set which is actually very similar to their test data set, which is kind of intuitive, right? Also, one of the things that they also identify is that they also tried out some of the demand reduction. So in their approach, actually, they might use a lot of channels. Their CNN features about 4096 dimension, 4096 dimension, right? And then actually they're in the same region. We are in the same region while we are using this binary code embedding. Just using the original high dimensional data set, it actually quite a lot of memory requirement. Also, there might be some other some noise, right? And then they tried out this TCA. So actually, this dimension reduction. They tried out. They reduced down the original 4000 dimension instead of 512, 250, and so on. And then they measure the accuracy. So the higher number is better. Higher number is better for the accuracy. So actually, they identify that up to if you look at in this case, they actually using some of the layer 6 of the convolution neural net architecture. So their accuracy kind of stable up to the 500, even the 200, even the 128. But after that, actually, they're up to this 256, the accuracy actually kind of very stable. But after that, actually, they are lowering they got the kind of low accuracy. So the main point is that it seems like CNN features actually kind of their design construct in a way they are very robust to their dimension reduction. So actually, even though they reduce down from the 4000 to this 256, they achieve they maintain the original accuracy, which is very good news. Also, we can also after that also we can adopt we can apply the binary code embedding. So that actually we can further improve this acceleration performance. Now I will talk about some other different techniques. This paper is saying that image classification and retrieval search techniques actually won. So I didn't really talk about the relationship between image search and the classification, but in a way, some of you may can identify that they're actually very similar to each other. So they're actually dedicated technique for the classification. We can using the deep learning or some other technique for the classification. But this paper point out that we can do their classification and image search in a kind of same framework, kind of unified framework. So to do that actually they use their external region proposal. Actually they at that time they didn't use this region proposal network. They just use the manually designed region proposal. So given the query image, they extract some of the region, and then they do the image. They do this nearest neighbor search. Nearest neighbor search is nothing but image search, right? Given a query region, query descriptor, we want to identify the nearby image or this nearby descriptors, right? Which is actually the main concept of image search. And then for basically given their query image, they identified this similar image that contain the similar regions. And so actually for this region they identify this one. For this region they identify these images. And then for the fused one actually, they actually consider this multiple region together and identify the image that contain both of the regions, right? But I'd like to point out that actually image search or this near neighbor search or the KNN, K nearest neighbor search is kind of the transductive learning. Some of you may heard about this transductive learning, right? So here I'd like to talk about induction and deduction. So you might know the induction deduction, right? Induction is that by looking at some of example, we wanted to actually approximating some of function, right? That also works very well with the example. That's induction, right? Deduction is that given this sum of function, we want to identify the certain value at a particular region, right? That's actually deduction, right? In other words, basic deduction is that from the general rule, we can actually talk about some of the specific idea, right? So and then transduction is that we don't do this kind of generalization. We reach this region. We reach this region from the example without going through this approximation. Approximation function. This is nothing but generalization. So for example, when we talked about the deep learning, we wanted to actually approximate some function for the classification of other tasks based on this training data, right? And then at the test time, given the query, we can actually talk about it. We can predict its label, something like that, right? So deep learning is training and this is testing, right? But transduction is kind of the image search and also this KNN. In other words, if you basically there in the when you perform image search, we have a lot of example in the DB, right? This actually you can treat that this the image or the data located within the this the DB, right? And then if, at a given query, I want to know that what are the actually nearby data, right? So that actually we identify the nearby the example, and then we can actually return that the nearby example. Also, the for example, for the case of the actually classification, given the query image, we identify the similar image, and then those identified similar image has a label of the cat, something like that. Then we can actually transfer those information from the nearby image to the query, and then we can say that that query image also there has this cat, right? That's the example of the transduction. But why I'm talking about this transductive learning? So one of the issues of deep learning is that when you have the problem of deep learning, it's very difficult to debug, right? So there could be some of the issues in terms of the generalizing function. Maybe the network architecture has just some of the limited power, or the example may be the low. That's why there are not many examples. That's why we got some of the incorrect results, right? But it's a little bit difficult, right? So that's the main problem of the deep learning. So that's why there has been the growing interest on the design this explainable AI, right? Along that line, this explainable AI, I think that image search or this KNN technique can have a certain potential, since given the query, we know that actually we can do the some classification, right? But we can actually mention that why we reach that inference at the test time by showing some of the nearby image, right? That way we can explain the techniques. So actually, I'm not going to talk about more along this line. But if you're interested, actually, why don't you look at why don't you think about it along this line? I think that this is actually one of the kind of the big issue along this image search, and then in terms of generalizing this image search to the different learning techniques. Okay, now let's talk about some other concept. This actually this technique also one of our lab member proposed this paper. This is regional attention based deep feature for the image search, image retrieval. So one of you may know the actual attention concept. Here actually we wanted to look at whether this object contains a ship or not, right? And then basically in that case we can identify the ship. But the question is that how can we identify the ship, right? In that case, we can actually showing the feature map, but actually we are showing we actually showing that in what regions of the feature map we paid more attention. So actually the higher the red value red color give you the more attention. So actually we attended more on this image on the feature, and based on that we can actually identify the correct label, right? That's the main concept of attention. So we want to actually apply this concept of attention or the saliency to the region, to the actual image search, right? And then at the time we know that actually RMAC-based, the region-based technique actually works quite well. So we wanted to apply this concept of attention concept to the region. So for some of region actually, when you talked about this RMAC, we didn't really talk about which one is more important than the others, right? But obviously we cannot treat them equally. So for that issue we can consider attention. So in some of the region, maybe it might have the attentive object, more salient feature, something like that. Then we give the more weight. And then if some of the region has just the background cluster, we give the lower accuracy and the lower weight in terms of attention. So by doing that, we actually I cannot talk about the details here. The main concept is that we also consider the RMAC unit that consider different regions, and then also we consider this kind of regional attention for each box, and then we combine them together, and then by using attention, we actually show that we achieve better accuracy by considering this kind of weight. Of course, there could be many other techniques, also the improvement by considering actually this kind of attention or some other factors. This was actually some of the recent technique. This is actually the deep learning based on the local feature. Basically, so far I talked about CNN feature, right? We can actually treat actually we can actually use it as a local feature or the global feature. But if you look at all of the most of the prior technique that I mentioned here, they are in a way the kind of global feature. So they didn't really design a kind of local specific feature. But this actually they talk about how we can design the feature descriptor that are more adapt to this local locality of in terms of image patch. So they mainly look at the aim. They mainly aim to propose a local descriptor. Also, and then they actually design the kind of dedicated loss function for extracting this very good local descriptor. But actually, their main idea is very similar to their main idea also based on this triplet loss, which I mentioned before. And then they also mentioned that in this paper, actually, they specifically claim that their accuracy actually better than the fifth, which actually we talked about early on. And then let me remind you what's the main concept of the triplet loss is that for designing triplet loss, which is also the ranking loss, given the anchor patch, we think about what's the positive, also what's the negative one, right? And then with this triplet loss, we wanted to learn a feature in a way that distance between anchor and its positive should be lower than the distance between anchor and negative, right? So basically, this feature within that feature, similar patches should have this higher similarity, which is actually indicating the lower distance in this definition of the distance. In this case, we can just using the Euclidean distance, L2 distance. And this is actually another illustration here. So they actually extract the different patch. We can just using the traditional traditional techniques. Actually, they use the DOG, difference of Gaussian, and then they look at the local maximum, and then based on that they can identify some sort of the local patch, right? They actually identify some of the local patch, and then actually here, given this the local actually for training, given this some of the anchor patch, they also identify this positive patch. They basically for this one they use the traditional shift-based matching technique or some other one, and then they actually for the other patch they also this anchor one, this also the positive one, and then this can be we actually denote them with the A1 P1, A2 P2, something like that, right? For design, then you can see that actually there's no relation between this first patch and there's no relation between this first patch, also the second patch, and so on. And then to designing this triplet loss, they wanted to identify the hard negative, which means that this patch does not match with this anchor, but actually somehow they're showing the very high similarity. It means that it's showing the very low distance. So actually they look at given this anchor patch A1, they consider all the distance between here, between A1, P2, P3, between A1, A4, and then they identify the smallest distance. Then you can see that since even though there is no relation between A1, P2, P3, P4, and some of the patch maybe in this case A1, P4, they're giving the very small distance, right? That's why we said hard negative. Also, we'll think about some the other direction. Given this P1, we also look at the distance between P1, A2, P1, A3, and so on. Also, they identify this pair of patches that gives the smallest distance. And then we can actually, in this case, suppose that A1, P4 showing the smaller distance out of this A1, P2, and so on. And then here, P1, A2 also showing the smallest distance between all the other patches between P1 and other anchors. And then out there also they pick the smaller distance, and then they treat it as between those two patches we pick the actual worst case. In other words, we know that that's negative, but somehow showing the smallest distance in the feature, right? And then we actually giving that triplet to the learning, so that we somehow designed our feature that gives the more lower distance for the anchor similar one, and gives the more wider distance between the anchor with this hard negative. That's the main concept of this technique. And then based on the actually once we identify this the local patch, and then we can actually extract the then we actually launch through our this trained network, and then actually we can use that this final feature, the convolutional CNN feature for the image search. You can see that actually when I talked about some of the early techniques, somehow when I talked about the deep learning in the early in some of the early technique, they are not fully the end-to-end trained of the system, right? Some of the system they use this kind of external component, right, which is not a deep learning based one. But here, as you can see, in this scheme, actually everything's kind of the end-to-end. So in other words, we consider different actually the factors in a deep learning method, so that we can achieve the best accuracy out of this trained data set. And then they also used some of the I'm not going to talk about the details on this network architecture, but you can see that their technique based on this convolution neural net, CNN technique. And also they tried out their feature with this prior this manually designed network, even though the SIFT. Actually, the root SIFT is one of the actually the improved the technique for the SIFT. This is actually their result. As you can see, also the higher value is better in terms of accuracy. They're showing that their result, their deep learning technique showing the better descriptor, better accuracy over the SIFT actually over the different context. So we can use we can design image search with a BOW backward visual word. Also we can consider backward visual word with the core expansion. Also the spatial verification, right? Along with the different combinations, actually, they show that their feature showing the much better result over the prior work, including the SIFT. So now, basically, one of the key messages here I can give you is that some of the deep learning descriptor, local descriptors, actually showing the better result over the actual SIFT. So far, I talked about different things. Actually, now we are getting close to the end of this lecture. So before I finish this talk, I'd like to talk about I'd like to summarize what we have talked about so far. We talked about the image search, right? You might recall that I showed this kind of the overall structure of image search, right? Along this line, first of all, we need to extract the feature, right? So that we talked about health corner detector, SIFT, also some of the recent CNN features. And then since a lot of techniques are actually based on the recent deep learning, I talked about the basic deep learning technique, the logistic regression that using also cross entropy, and deep learning also they're optimized with the stochastic gradient descent. And then I talked about CNN convolutional neural net, and then some of the recent CNN features that designed with the triplet loss. Also we can consider region and attention. There could be many other factors, and then now it's your turn to think about those issues for your project. Also, I talked about the backward visual word as an aggregation model from these local descriptors. Along the line, we can use k-means clustering or the product quantization. I briefly talked about the blood, right? Blood basically the kind of extension to the backward visual word model. Also, they consider this delta, right? And then we talked about some of the re-ranking or the post-processing model with the core expansion or spatial verification. Also, I talked about to localize our search area. We talked about inverse index, and then for that we can use the product quantization, also the inverse multi-index. And finally, I talked about the hashing technique with the unsupervised or the supervised techniques. These are actually the main kind of summary of what we have talked about so far. But nonetheless, there are a lot of issues. So a lot of cases for the image search, those technique works well for the kind of rigid and planar, also these textured cases, images, right? But when you apply those techniques with some other images with the texture list, in this case, since there are not much texture, in other words, not much information, it's very difficult to extract the meaningful features. Also, we have actual 3D objects. Actually, there are shapes. Due to the shapes, there are a lot of variation, right? So we need to think about actually how we can consider those 3D shapes and consider that for improving improving the accuracy. Also, the reflective surfaces. We didn't really talk about the material issues, but depending on the materials, actually, basically some of the material may be very reflective. Also, this transparent, right? But I just need to think about it, how we can actually handle those kind of images with different materials for achieving the better accuracy. Also, there could be a lot of cases with this non-rigid model. For example, further the application of the person identification. For that case, person is not rigid, right? And then we need to think about it. The kind of the moving people. We need to think about what a technique for that kind of this person identification. Also, I didn't so far I mainly focus on the image search, right? But we can actually extend those techniques to the video. But there are a lot of challenges. In the end, there are large-scale video retrieval problem. Basically, there could be 5 billion shared video at YouTube, and then in each video actually comes with about 30 frames or the 30 images per second, right? Then we actually have a much more challenging issues in terms of the performance and memory or the accuracy. There are a lot of issues. So I'd like to actually talk about some of the applications, also the extension of the research technique. But I decided not to talk about each individual technique, but actually I grabbed some of this corporate paper from the ACM, ICMR, the Multimedia Retrieval Conference. Actually, at the conference they listed some of the topics, right? Then you can see that the hashing, indexing of some of multimedia, right? So you can, in this class we may talk about image, right? Among the multimedia, about hashing, indexing, but we can always think about it. We can always we can look into how we can actually design this hashing, indexing, some other multimedia one. Also, we can think about it multimodal or cross-modal. Here actually I may talk about the just general image, but what are the actual search from the sketch to just a regular RGB image, right? That could be the cross-modal. Also, we can think about it. We want to identify some of the result with the image with the text, right? Then we think about this multimodal issue. And then along that cases, what are the descriptors, also the similarity metrics. In this class, we talk about some of them, but there are a lot of issues, right? Also, we didn't really talk about event detection, right? In some of the cases, we wanted to identify the image or video that contain the similar event, right? And then also that could be another issue. Also, once we identify the image to the viewer, and then the viewer may like that the result. Also, people may not like it, right? And then the user may actually give another feedback, right? And then actually there could be a lot of issues how we can handle those kinds of the feedback. Also, in general sense, that's actually the human-computer interaction. We actually haven't talked about those issues, but there are a lot of issues. Along that line, what are the query model of the language? Also, depending on the application, sometimes we wanted to have we wanted to identify the very fine-grained actual visual search, right? Some of cases I want to identify the image with containing animal, right? But some of cases I wanted to identify the image with dog. In other words, I designed more finer actually a category, right? In some of cases, I wanted to identify the image contains not just general dog, a particular breed of dog, like the Maltese, something like that, right? Then actually, what are the descriptor and techniques that considering this kind of fine-grained search. And then we also need to think about what are the summarization. We can identify a set of image, also a set of video. But showing those a lot of the results to the viewer, it takes a lot of time for user to understand those results, right? Along that line, we need to think about the summarization, also what is a good visualization techniques. And then right now, actually, we are using a lot those image search on the mobile, also some even actually there could be the many other future platform like the autonomous vehicle, right? Then what are actually the visual search technique on that kind of mobile cases, also this future platform. There are a lot of issues, but I leave it to you as your project topics. Okay, today I talked about the CNN-based, some of recent CNN-based approaches that consider different regions or the attention local feature. I talked about some of the application feature work, And and then I wish that so far I talked about a lot of materials of the image search, and then I talked about some of the limitation and future work. I wish that those techniques, my lecture actually helpful for you to learn the basic materials so that now you can do your own project. And thank you so much for listening. I wish that you can actually have a very great semester here today. Thank you. Bye.